The journey begins. A photon's birth. In the heart of a star, deep within a furnace burning at 15 million degrees, our story begins. Not with a grand explosion, but with something quieter, a gentle collision between two hydrogen atoms. They press together under unimaginable pressure, fusing into helium, and in that moment of transformation, a single photon of light is born. It emerges as a gamma ray, carrying tremendous energy, yet it is so small that 100 billion of them would fit on the head of a pin. But this photon cannot simply leave. The star's core is impossibly dense. A single sugar cube's worth of this material would weigh as much as 15 elephants. Our photon begins to move, traveling at the speed of light, which is 186,000 miles every second. Yet within 1 centimeter, less than half an inch, it collides with another particle. The photon is absorbed, then re-emitted in a random direction. It happens again and again. This is the photon's first truth. Despite being the fastest thing in the universe, it is trapped in an endless maze. Scientists call this the random walk, and our photon will take this stumbling, chaotic journey for thousands of years. Some photons born in our own sun's core may wander for 100,000 to 1 million years before finally reaching the surface, a distance that, if they could travel straight, would take only 2.3 seconds to cross. With each collision, our photon changes. It might split its energy with the particle that absorbed it, emerging weaker, with a longer wavelength. A gamma ray becomes an X-ray. An X-ray becomes ultraviolet light. The photon gradually cools as it drifts outward through the star's radiative zone, where energy moves only through radiation, each photon passing its light to the next in an ancient relay that has continued since the star first ignited. Time passes differently here. For the photon, traveling at light speed, time itself stands still. This is what Einstein showed us. From the photon's perspective, if it could have won, the entire journey happens in a single instant, beginning and end collapsed into now. But from the star's perspective, from our perspective, millennia slowly turn. Eventually, our photon reaches a new realm, the convection zone. Here, the star's material churns and boils like water in a pot, carrying our photon upward in vast currents of plasma heated to millions of degrees. The journey becomes faster, more purposeful. What took 100,000 years in the core takes only weeks here, as the photon rides these titanic columns of rising gas toward the surface. And then, finally, it breaks free. The photon crosses the photosphere, the visible surface of the star, and enters the open darkness of space. No more collisions. No more delays. For the first time in ages beyond counting, the photon travels in a straight line, and the real journey begins. Into the cosmic ocean. The photon's flight. Our photon is free now, sailing through the void, and space is far more empty than most of us imagine. If you could hold out your hand in the space between stars, fewer than one atom would exist in each cubic centimeter. An emptiness so profound that the best vacuums we can create on Earth are still 1,000,000 times denser. The photon travels through this near-nothingness, undisturbed, at its eternal speed. 8 minutes pass. 8 minutes and 20 seconds to be precise. And if our photon left a star like our own sun, it would already be crossing the orbit of Earth. This is the distance light travels between the sun and our world, 93 million miles, a span we call an astronomical unit. Ancient photons from our sun, born when humans first painted on cave walls, would have only just reached the outer edges of our solar system, beyond where Pluto drifts in its slow orbit. But our photon is not headed for a nearby planet. It continues outward, past where the star's family of worlds circle, into the space between stars. Here, time dilates into scales that challenge human understanding. For years pass, then more. If our photon's path happened to aim toward the nearest star to our Sun, Proxima Centauri, it would take 4.24 years to arrive, a distance of 25 trillion miles. Yet our photon maintains its speed perfectly. Unlike a thrown ball or a spacecraft, a photon never slows down, never tires. It will travel at exactly 186,000 miles per second until something stops it. As the photon journeys through interstellar space, it carries with it a specific color, a specific wavelength, determined by its energy. Perhaps it has cooled to become visible light, maybe yellow-orange like our Sun's most common photons, with a wavelength of about 600 nanometers. A nanometer is 1/1000th of a meter, so small that a single human hair is about 80,000 nanometers wide. This wavelength, this color, is like the photon's fingerprint, encoding the story of where it came from and what happened in the star's atmosphere as it escaped. Decades pass. Centuries. The photon crosses distances so vast that entire civilizations could rise and fall in the time it takes to traverse them. Light from the stars we see at night left those distant suns generations ago. Some of those stars may have already died, their light still reaching us like messages from ghosts. The brightest star in our night sky, Sirius, sends us photons that are 8.6 years old by the time they touch our eyes. The photon is a wave and a particle simultaneously, one of the universe's most elegant mysteries. It ripples through space like a wave on water, yet when it finally strikes something, it arrives as a discrete packet of energy, a quantum. This dual nature puzzled scientists for centuries. How could light be both? The answer is that light is simply light, behaving as both depending on how we observe it, neither wave nor particle, but something more fundamental that we've only recently begun to understand. Our photon travels on, year after year, through clouds of gas and dust scattered between the stars. Sometimes these clouds are thick enough to scatter the photon's path slightly, bending its trajectory by fractions of a degree. Blue light scatters more easily than red. This is why Earth's sky appears blue, as sunlight's blue wavelengths bounce through our atmosphere, while red wavelengths pass straight through to give us crimson sunsets. If our photon happens to be blue, it may dance and scatter through these cosmic nebulae, its path becoming less straight, more wandering. Thousands of years into its journey now, the photon carries its energy across the galaxy. It has no mass, weighing absolutely nothing, yet it carries momentum, capable of exerting the tiniest push on anything it strikes. Scientists have even proposed using this pressure from starlight to propel spacecraft on vast journeys, letting photons from the sun push against enormous reflective sails. A photon the size of... Well, a photon has no size in the traditional sense, but its effect, multiplied across billions of its companions, could one day carry our vessels to distant worlds. The photon continues, patient and eternal, crossing the spiral arm of a galaxy, moving through a cosmos that is itself expanding. And somewhere ahead, after a journey measured not in hours or years but in millennia, something waits. Perhaps a planet. Perhaps an eye. Perhaps merely another molecule of dust. But for now, in this moment, the photon simply is, traveling unchanged through the infinite dark. Through the galactic sea. The photon's odyssey. Our photon drifts through a galaxy containing 200 billion stars, each one a furnace like the one from which it was born. The Milky Way, if we could see it from above, spirals like a great pinwheel, 100,000 light-years from edge to edge. Our photon, traveling for millennia now, has crossed perhaps a tiny fraction of this distance. A single light-year, maybe 10, maybe 100. The scale is humbling. At its current pace, it would take 100,000 years to cross from one side of the galaxy to the other, if its path were so perfectly straight. But something remarkable happens as the photon travels. The universe itself is expanding. Space stretches like the surface of an inflating balloon, and as it does, the wavelength of our photon stretches with it. A photon that left a distant galaxy as blue light might arrive at Earth as red light, shifted toward longer wavelengths by this cosmic expansion. Scientists call this redshift, and it's how we know the universe is growing larger. The farther a photon travels, the more the space through which it moves has expanded, and the more its light is stretched toward the red end of the spectrum. Our photon maintains its energy against the cold of space, which hovers at a temperature of just 2.7 degrees above absolute zero, that's minus 270 degrees Celsius, or minus 454 degrees Fahrenheit. This faint warmth is the afterglow of the Big Bang itself, the cosmic microwave background radiation that fills all of space. In this frozen void, our photon is a tiny spark of warmth, a messenger carrying energy from a star's heart. Time continues its patient march. The photon may encounter a dust grain, something only a few micrometers across, about the width of a bacterium. If it does, it will be absorbed, its energy converted to heat, warming that speck of dust by an infinitesimal amount. The dust grain will then re-emit that energy as infrared light. A photon of lower energy, longer wavelength, invisible to human eyes but detectable by specialized instruments. This is how stars heat the clouds of gas and dust around them, each photon a tiny courier of thermal energy. Or perhaps our photon avoids the dust and continues onward. As it travels, it passes through the galaxy's magnetic fields, invisible lines of force that thread through space like a cosmic web. These fields are incredibly weak, about 100,000 times weaker than a refrigerator magnet, yet they stretch across light years. Our photon, having no electric charge, passes through them undisturbed. But if it were traveling alongside a cosmic ray, a charged particle racing through space, it would witness that particle's path being bent and twisted by these magnetic currents, while the photon itself continues straight and true. Tens of thousands of years into its journey, our photon carries information encoded in its very existence. Astronomers can examine a photon's wavelength and, from that single piece of data, determine what element produced it. Each atom, hydrogen, helium, oxygen, iron, emits photons at specific, characteristic wavelengths when excited. Hydrogen produces a red photon at exactly 656.3 nanometers. These spectral lines are like fingerprints, and they allow us to know what distant stars are made of, though we've never touched them. Our photon is a letter written in the language of light, carrying news from its stellar home. The photon also carries a kind of memory of its star's motion. If the star was moving toward an observer, the photon's wavelength would be slightly compressed, blue-shifted. If moving away, slightly stretched, redshifted. This is the Doppler effect, the same phenomenon that makes an ambulance siren sound higher-pitched as it approaches and lower as it recedes. From a single photon, we can read not just what made it, but how fast its source was moving. The universe reveals itself through light. As our photon continues through the darkness, it remains fundamentally unchanged by its journey. Unlike matter, which can decay or degrade, a photon in empty space is eternal. It does not age. It does not weaken on its own. The photon that left a star 1,000,000 years ago arrives with the same energy it had at birth, minus only what the universe's expansion has gently borrowed. This stability is what makes light such a perfect messenger. It brings us news from the past, unaltered, authentic. And so the photon travels on, a single quantum of light in an ocean of darkness, moving through a galaxy that rotates once every 200 million years. Our own sun has orbited the galactic center only about 20 times since it formed, 4.5 billion years ago. The photon witnesses none of this rotation. It moves too fast, its journey too brief on cosmic scales. But it is part of this great spiral nonetheless, one photon among countless trillions, all streaming outward from their stellar sources, filling the galaxy with light. Somewhere ahead, its destination waits. But for now, the photon simply continues, tireless and true, through the vast and patient dark. Across the depths. The photon's persistence. Our photon has traveled now for ages beyond easy counting, and it moves through a galaxy that is not as empty as it first appears. Between the stars drift vast molecular clouds, some of them hundreds of light-years across, filled with hydrogen gas so diffuse that it contains only a few hundred atoms per cubic centimeter. Still a better vacuum than we can create in laboratories, yet thick enough to interact with passing light. These clouds are the nurseries where new stars are born, where gravity slowly pulls gas together over millions of years until fusion ignites and another stellar furnace begins to burn. If our photon passes through one of these clouds, something subtle occurs. The photon may encounter a hydrogen atom and give it a gentle push, transferring some of its momentum. This process is called radiation pressure, and though each individual photon exerts only the tiniest force, about equivalent to the weight of a single bacterium spread across an area the size of a tennis court, when billions upon billions of photons stream through these clouds, they can actually push the gas, sculpting these nebulae into beautiful shapes and even preventing them from collapsing too quickly under their own gravity. Light, weightless as it is, can move mountains of gas. The photon's energy can be precisely calculated using a simple relationship discovered by Max Planck. The energy of any photon equals Planck's constant, a very tiny number, about 6.6 times 10 to the negative 34th joule-seconds, multiplied by the photon's frequency. Higher frequency means more energy. A gamma-ray photon carries millions of times more energy than a radio wave photon. Our photon, perhaps now a gentle yellow or orange visible light, carries just enough energy to trigger a chemical reaction in the retina of an eye, should it ever reach one. This is the quantum nature of light. Energy comes in discrete packets, not in continuous streams. As the photon continues, it travels through what astronomers call the interstellar medium, the thin soup of gas, dust, and cosmic rays that fills the space between stars. About 90% of this material is hydrogen, the simplest and most abundant element in the universe. The remaining 10% is mostly helium, with trace amounts of heavier elements like carbon, oxygen, and iron. All of them forged in the cores of ancient stars that exploded as supernovae, scattering their enriched material across the galaxy. Our photon's journey takes it through this recycled stardust, the building blocks of future worlds. Millions of years might pass in the photon's journey. Millions of years of our time, though for the photon itself, time remains frozen at zero. If this photon left a star at the far side of our galaxy, it would travel for 100,000 years before reaching the other edge. If it left a star in the Andromeda galaxy, our nearest large galactic neighbor, it would travel for 2.5 million years before arriving at the Milky Way. These distances strain comprehension. Andromeda contains roughly 1 trillion stars, and each of those stars sends out photons in every direction, creating a sphere of light that expands outward at the speed limit of the universe. Our photon knows nothing of these vast scales. It simply moves, and in moving, it demonstrates one of Einstein's most profound insights, that light always travels at the same speed relative to any observer, no matter how fast that observer is moving. You could chase a photon in a spacecraft traveling at 99% the speed of light, and that photon would still pull away from you at exactly 186,000 miles per second. This cosmic speed limit isn't just a property of light. It's a fundamental feature of spacetime itself, woven into the very fabric of reality. As the photon journeys on, it might pass through regions where space itself is curved by gravity. A massive object like a star or a black hole bends spacetime the way a bowling ball creates a depression in a stretched rubber sheet. When light passes near such an object, its path curves, following the geometry of warped space. This phenomenon, called gravitational lensing, can cause distant objects to appear distorted or even multiplied. We sometimes see multiple images of the same galaxy because its light has taken different curved paths around an intervening massive cluster. Our photon, if it passed near a sufficiently massive object, would have its trajectory gently bent, yet from the photon's perspective, it would still be traveling in a perfectly straight line through curved space. The photon also carries a property called polarization, the orientation of its oscillating electric and magnetic fields. Light waves vibrate in specific directions perpendicular to their travel, and this orientation can be altered when light reflects off surfaces or passes through certain materials. Sunlight reflecting off water becomes partially polarized, which is why polarized sunglasses can reduce glare. Some animals, like mantis shrimp and certain birds, can see polarized light, giving them information about their environment that's invisible to human eyes. Our photon's polarization is like a hidden dimension of its existence, data encoded in the orientation of its wave. Onward the photon travels, through the star-strewn spiral arms, through the darkness between, carrying its precise wavelength, its specific energy, its directional momentum. It is both infinitely simple, just light, and infinitely complex in what it represents, a quantum of electromagnetic radiation, a ripple in fields that permeate all of space, a messenger from the past, a carrier of information, a wanderer through curved spacetime. The journey is not yet complete. Somewhere ahead, across distances that dwarf human understanding, an end awaits. But between this moment and that destination lies only more darkness, more space, more time, and the photon's patient, unwavering persistence. The long crossing. The photon's silent voyage. Our photon has now traveled distances that render familiar measures meaningless. Perhaps it has crossed a significant fraction of the galaxy, or perhaps it journeys between galaxies, through the great voids that separate these islands of stars. These voids are the largest structures we know, empty regions spanning hundreds of millions of light-years, containing almost no galaxies, almost no matter. Just darkness, and the occasional photon like ours, crossing from one shore to another across an ocean of nothing. The photon moves through these voids at its constant speed, but something remarkable happens to it during such vast journeys. Because the universe is expanding, and has been since the Big Bang 13.8 billion years ago, the space through which our photon travels is literally stretching. As space expands, it carries galaxies apart like dots on an inflating balloon. Our photon, stretched along with space itself, gradually loses energy. A photon that began its journey as visible light might, after billions of years crossing cosmic distances, arrive as a microwave or even a radio wave. The universe's expansion is gentle but inexorable, cooling the light of distant stars as it travels. Yet the photon remains, in essence, immortal. Unlike particles of matter which can decay, a free neutron, for instance, will decay into a proton, electron, and neutrino in about 15 minutes. A photon in empty space will never decay. It will travel forever, or until it encounters something. In principle, a photon created in the first moments after the Big Bang could still be traveling through space today, 13.8 billion years later, unchanged except for the stretching imposed by cosmic expansion. The universe is filled with ancient light, photons older than Earth, older than the Sun, older than any structure we can see. As our photon journeys through intergalactic space, it travels through what we call the cosmic web, a vast network of dark matter and gas that connects galaxies like threads in a tapestry. Dark matter is invisible. It doesn't emit, absorb, or reflect photons, which is why we call it dark. Yet it makes up about 85% of all matter in the universe. Our photon passes through regions dense with dark matter and never interacts with it at all. Dark matter responds only to gravity, pulling on normal matter and shaping the large-scale structure of the cosmos, while remaining utterly transparent to light. Our photon is blind to most of the universe's mass. The photon's journey might take it past a pulsar, a rapidly spinning neutron star that beams radiation into space like a cosmic lighthouse. Pulsars can rotate hundreds of times per second, and the fastest known pulsar spins at 716 rotations per second. These stellar remnants are incredibly dense. A single teaspoon of neutron star material would weigh about 1 billion tons, as much as a mountain compressed into something you could hold in your hand. If our photon passed near such an object, it would witness electromagnetic radiation being swept across space in a precise, repeating pattern, though the photon itself would continue undisturbed, adding its small light to the pulsar's brilliant beam. Time stretches on. Hundreds of thousands of years. Millions. The photon knows no fatigue, no boredom, no sense of the immensity of its journey. It simply is, moving through the void. In its reference frame, the entire journey, from creation to eventual absorption, happens in literally zero time. This is the paradox of light-speed travel. From our perspective, the photon's journey might span eons, but from the photon's own perspective, if we could imagine such a thing, its entire existence is a single, timeless instant. Birth and death are the same moment, stretched across billions of miles and millions of years by the strange geometry of spacetime. As the photon travels, it carries with it a specific amount of angular momentum, a property related to the rotation of its electromagnetic fields. Photons can have two states of circular polarization, left-handed or right-handed, describing the direction their fields spiral as they propagate. This property is called spin, and for photons, the spin is always one, in the quantum mechanical sense. This spin is conserved throughout the photon's journey. It's an intrinsic property that cannot change unless the photon interacts with matter. Like a figure skater pulling in their arms to spin faster, the conservation of angular momentum is one of the universe's fundamental accounting rules, and every photon obeys it. Our photon might encounter a planet during its journey, perhaps a rogue world, ejected from its solar system billions of years ago, now wandering alone through interstellar space. There may be billions of such orphan planets in our galaxy, worlds without suns, drifting through the darkness. If our photon strikes such a planet's surface, it might be absorbed, its energy converted to a tiny, imperceptible bit of warmth. Or it might reflect off ice or rock, scattered into a new direction, continuing its journey with a slightly different trajectory but the same speed, the same essential nature. The photon crosses vast stretches of space where the density of matter is so low that it could travel for light-years without encountering a single atom. In the emptiest voids, there might be only one atom in every cubic meter, a volume about the size of a large refrigerator. Our photon passes through these regions untouched, a solitary traveler in an almost perfect vacuum, carrying its message from a long-dead star or a star still burning bright, depending on the length of its journey. And still it travels. Still it moves. The universe around it slowly evolves. Stars are born and die, galaxies collide and merge, the cosmic expansion continues its patient work. But the photon persists, unchanged in its fundamental nature, a quantum of light crossing the abyss, destined for some distant encounter it cannot anticipate, moving through the darkness with neither purpose nor awareness, simply obeying the laws that govern all things. Through darkness and light. The photon's endurance. Our photon drifts onward through the cosmos, and as it travels, it passes through regions shaped by forces both visible and invisible. The galaxy through which it moves is held together by gravity, the weakest of the four fundamental forces of nature, yet the one that dominates at cosmic scales. Gravity is about 10 to the power of 36 times weaker than the electromagnetic force that governs how photons interact with charged particles. A small magnet can lift a paperclip against the gravitational pull of the entire Earth, yet gravity's patient accumulation over vast distances binds galaxies together and shapes the architecture of the universe. The photon's path might take it near a stellar nursery, where new stars are forming from collapsing clouds of gas. These regions glow with the light of newborn stars, some of them so young they haven't yet cleared away the cocoons of dust that surround them. The most massive of these infant stars burn with incredible intensity. A star 100 times the mass of our Sun shines with nearly 1 million times the Sun's luminosity. These stellar giants live fast and die young, exhausting their nuclear fuel in just a few million years, while smaller stars like our Sun can burn steadily for 10 billion years or more. Our photon, born perhaps from a star somewhere in between, carries within its wavelength clues to its parent star's temperature and mass. As it journeys through space, the photon is surrounded by other forms of light invisible to human eyes. Radio waves, with wavelengths measured in meters or even kilometers, carry information from distant quasars and pulsars. Microwaves fill the universe with the faint afterglow of creation. Infrared light reveals the heat of objects too cool to glow visibly. Then comes visible light, the narrow band our photon might occupy, spanning wavelengths from about 380 nanometers for violet to about 740 nanometers for deep red. Beyond lies ultraviolet, X-rays, and gamma rays, each more energetic than the last. All of these are photons, all traveling at the same speed, differing only in their energy and wavelength. Our photon is one note in an infinite electromagnetic symphony. The visible spectrum that human eyes can perceive represents less than 1/10,000,000,000th of the entire electromagnetic spectrum. We evolved to see this particular slice of light because our Sun emits most of its energy in these wavelengths, and Earth's atmosphere is transparent to them. If we had evolved under a different star, or in a different environment, we might see radio waves or infrared instead, and the universe would look entirely different. Our photon, if it falls within visible wavelengths, is part of this narrow window, a color that exists not because the universe chose it, but because eyes chose to perceive it. Time continues its forward march, forward for us, frozen for the photon. The photon might now be crossing through a region influenced by a supernova remnant, the expanding shell of gas and energy left behind when a massive star exploded. Supernovae are among the brightest events in the universe. For a brief time, a single exploding star can outshine an entire galaxy of hundreds of billions of stars. The shock wave from such an explosion travels through space at speeds of thousands of kilometers per second, compressing and heating the interstellar medium. If our photon crosses through such a region, it moves through gas heated to millions of degrees, glowing with the energy of stellar death, yet the photon itself passes through undisturbed, its path straight and true. These supernovae serve a vital cosmic purpose. They are the forges where elements heavier than iron are created. During the normal life of a star, fusion can build elements up to iron, but creating anything heavier requires more energy than fusion releases. Only in the violent explosion of a supernova, or in the collision of neutron stars, are conditions extreme enough to forge gold, platinum, uranium, and all the other heavy elements. The atoms in our bodies, the calcium in our bones, the iron in our blood, were created in such stellar explosions billions of years ago. Our photon travels through a universe built from the ashes of dead stars. As the photon continues, it demonstrates a principle that governs all waves: interference. When two photons of the same wavelength meet, they can interfere with each other. If their wave peaks align, they constructively interfere, creating a brighter combined wave. If a peak meets a trough, they destructively interfere, and the light cancels out. This wave behavior allows light to create interference patterns, the alternating bands of light and dark that convinced scientists in the 19th century that light was a wave. Yet each photon, when it finally strikes something, arrives as a particle, a discrete quantum. Our photon is both, simultaneously, neither fully wave nor fully particle, but something that transcends these classical categories. The photon also carries information about the magnetic field through which it has traveled. In a phenomenon called Faraday rotation, the polarization of light can be rotated as it passes through a magnetic field embedded in plasma. By measuring this rotation, astronomers can map the invisible magnetic fields that thread through galaxies and between them. Our photon, if it has passed through such regions, bears this subtle signature: a slight twist in its polarization, a record of the magnetic landscape through which it has journeyed. Every photon is not just a carrier of energy, but a carrier of history. And so the photon continues its ancient voyage, through regions thick with gas and regions empty of all but space itself. It passes through zones shaped by stellar winds and supernova remnants, through the invisible architecture of dark matter, through magnetic fields that stretch across light years. It travels toward some unknowable destination, neither hurrying nor delaying, simply being what it is, a quantum of light in an immense and darkened universe, moving through the void with perfect constancy. The darkness remains vast. The journey continues. And the photon endures. Through the cosmic tapestry. The photon's testament. Our photon has traveled now through epochs of cosmic time, and the universe through which it moves is not static but dynamic, ever-changing on scales both vast and intimate. The stars it passes are themselves in motion. Our own sun orbits the center of the Milky Way at a speed of about 515,000 miles per hour, carrying Earth and all the planets with it. At this velocity, it takes approximately 230 million years to complete one galactic orbit. The last time our Sun was in its current position in the galaxy, dinosaurs had not yet appeared on Earth. Our photon, depending on its direction of travel, might be moving with this galactic rotation or against it, adding or subtracting from the great cosmic dance. The center of our galaxy, around which all these stars orbit, harbors something extraordinary. A supermassive black hole called Sagittarius A*, containing the mass of about 4 million suns compressed into a region smaller than the orbit of Mercury. Black holes are perhaps the universe's strangest objects, regions where gravity is so intense that not even light can escape. If our photon's trajectory took it too close to such an object, it would be drawn inexorably inward, crossing the event horizon, the point of no return, and vanishing from the observable universe forever. But our photon travels elsewhere, far from such gravitational prisons, its path taking it through safer regions of space. As the photon journeys, it exists in a universe that is not only expanding but accelerating in its expansion. In 1998, astronomers discovered that distant galaxies are receding from us faster and faster, driven by a mysterious force they call dark energy. This dark energy makes up approximately 68% of all the energy in the universe, far more than all the matter, both normal and dark combined. We don't know what dark energy is, only that it acts as a kind of anti-gravity, pushing space apart. Our photon travels through a universe increasingly dominated by this mysterious force, a cosmos that will, in the far future, see galaxies separated by distances so vast that their light will never reach each other. The photon carries its energy according to a precise relationship. Its wavelength multiplied by its frequency equals the speed of light. A photon with a short wavelength oscillates rapidly, high frequency, high energy. A photon with a long wavelength oscillates slowly, low frequency, low energy. This inverse relationship is fundamental. Our photon, whatever its wavelength, vibrates at a specific frequency, perhaps 500 trillion times per second if it's yellow-green light, the frequency to which human eyes are most sensitive. 500 trillion oscillations every second, for millions of years, for the entire duration of its journey through space. As it travels through the galaxy, the photon might pass through regions enriched by stellar winds, streams of particles blown off the surfaces of stars. Our Sun ejects about 1 million tons of material into space every second through the solar wind, a continuous outpouring of charged particles that streams through the solar system at speeds of hundreds of kilometers per second. More massive stars can lose mass even more dramatically. Some giant stars shed material at rates millions of times greater than our Sun. Our photon passes through this tenuous stellar breath, these rivers of ionized gas flowing between the stars, yet remains unaffected by the charged particles streaming past it. The photon also travels through a universe filled with neutrinos, ghostly particles that barely interact with anything. About 65 billion neutrinos from the Sun pass through every square centimeter of your body every second, day and night, streaming through the Earth itself as though it weren't there. These neutrinos are produced by the same fusion reactions that create photons in stellar cores, but unlike photons, which take thousands of years to escape the Sun's interior, neutrinos escape almost instantly because they interact so weakly with matter. Our photon has companions in its journey, countless neutrinos racing alongside, both born in stellar furnaces but traveling very different paths to reach the cosmos beyond. The speed at which our photon travels, 186,000 miles per second, or about 300 million meters per second, is not just the speed of light, but the speed of causality itself. This is the maximum rate at which any information or influence can propagate through the universe. Nothing can travel faster. It's not a technological limitation but a fundamental property of spacetime. If something could exceed this speed, it would violate causality, effects could precede their causes, and the logical structure of the universe would break down. Our photon travels at the universe's ultimate speed limit, the boundary between possible and impossible. As the photon continues through space, it moves through regions where the fabric of spacetime itself ripples with gravitational waves, distortions in space caused by accelerating massive objects. When two black holes spiral together and merge, they send ripples radiating outward through spacetime at the speed of light. These gravitational waves stretch and compress space itself as they pass, by amounts almost impossibly small. Detectors on Earth measure distortions smaller than a proton's width. Our photon, traveling through these rippling waves of spacetime, rides the gentle undulations of space itself, though the effect is far too subtle to alter its path noticeably. Onward the photon travels, through this universe of black holes and dark energy, of stellar winds and neutrino streams, through space that expands and ripples, through a cosmos more strange and beautiful than our ancestors could have imagined. The photon knows none of this complexity. It simply moves, as it has moved since its birth, as it will move until something stops it. It is a simple thing in a complicated universe, a single note of light in an orchestrated cosmos, traveling through the dark with neither purpose nor awareness. But it carries something precious nonetheless: energy, information, a connection between the place it left and the place it goes. It is a messenger, even if unaware. And its message is this: the universe is vast, but light connects it all. The journey continues, through the infinite dark, toward whatever waits ahead. The endless horizon. The photons approach. Our photon has now traveled distances that seem to exceed imagination itself, and yet it moves through a universe that is larger still. The observable universe, the portion of space from which light has had time to reach us since the Big Bang, stretches approximately 46 billion light-years in every direction. This is larger than 13.8 billion light-years, the age of the universe, because space itself has been expanding during the time light has been traveling. Our photon, wherever it is in its journey, exists somewhere within this vast sphere of the observable, though beyond our horizon lie regions of space we can never see, galaxies whose light will never reach us because the expansion of space carries them away faster than light can travel toward us. The photon travels through a universe governed by the laws of thermodynamics, and one of these laws ensures that entropy, disorder, always increases. The universe began in a state of extraordinarily low entropy, highly ordered, concentrated in the incredibly hot, dense conditions of the Big Bang. As it expands and cools, entropy increases. Stars burn, releasing their ordered nuclear energy as disordered heat and light. Our photon is part of this process, a carrier of energy flowing from ordered systems to disordered ones, from hot stars to cold space. Eventually, in the unimaginably distant future, the universe may reach a state of maximum entropy, where all energy is evenly distributed and nothing can happen anymore, a scenario called heat death. But that lies trillions upon trillions of years ahead. As our photon journeys, it moves through space at a rate that can be expressed in more familiar terms. In 1 year, light travels about 5.88 trillion miles, a distance we call 1 light-year. In the time it takes you to read this sentence, perhaps 5 seconds, our photon has traveled 930,000 miles, enough to circle Earth's equator about 37 times. In 1 day, light travels about 16 billion miles, roughly the distance from the Sun to beyond the orbit of Neptune. These distances accumulate. A photon traveling for just 1,000 years crosses nearly 6 quadrillion miles, 6 followed by 15 zeros. Our photon has perhaps been traveling far longer. The photon also exists in a quantum universe where certainty gives way to probability. Before it interacts with something, we cannot say with absolute precision where the photon is. We can only describe the probability of finding it in various locations. This is not a limitation of our knowledge, but a fundamental property of quantum mechanics. The photon exists as a wave of probability, spread across space, until the moment it is detected, at which point this wave function collapses and the photon is found in one specific place. Schrödinger's famous thought experiment about a cat both alive and dead was meant to illustrate how strange this is. Our photon travels as a ghostly probability until the universe demands it become real. As it continues through space, the photon might pass near a planet orbiting a distant star. Our galaxy alone likely contains hundreds of billions of planets, and in the observable universe, there may be more planets than stars, perhaps 2 trillion planets, a 2 followed by 24 zeros. Many of these worlds orbit in the habitable zones of their stars, at distances where liquid water could exist on their surfaces. Some of these planets may harbor life, perhaps even intelligent life, looking up at their own night skies and wondering about the photons reaching their eyes from distant suns. Our photon continues past these possibilities, neither knowing nor caring what worlds might exist nearby. The photon's electromagnetic nature means it consists of oscillating electric and magnetic fields, perpendicular to each other and to the direction of travel. These fields regenerate each other as they propagate. The changing electric field creates the magnetic field, and the changing magnetic field creates the electric field, in an endless cycle that allows the photon to travel indefinitely through empty space without any medium to support it. In the 19th century, scientists believed light required a medium they called the luminiferous ether, but experiments proved this ether didn't exist. Light needs nothing. It moves through pure vacuum as easily as through anything, self-sustaining, self-propagating, a wave that carries itself. Our photon travels through a universe that is remarkably flat on large scales. When cosmologists measure the geometry of space, they find that, to extraordinary precision, the universe has zero curvature. Parallel lines remain parallel even across cosmic distances. If the universe had positive curvature, like the surface of a sphere, parallel lines would eventually converge. If negative curvature, like a saddle, they would diverge. But measurements show the universe is flat to within less than 1% deviation. This flatness is puzzling. Why should the universe have exactly, or nearly exactly, zero curvature? The theory of cosmic inflation, which proposes a period of exponential expansion in the universe's first fraction of a second, provides one explanation. Inflation stretched the universe so large that any initial curvature became negligible, the same way Earth's surface appears flat when you're standing on it. The photon also travels through a universe where quantum entanglement creates mysterious correlations between distant particles. Two photons can be entangled such that measuring the polarization of one instantly determines the polarization of the other, even if they're separated by light years. Einstein called this spooky action at a distance, and was deeply troubled by it, but experiments have confirmed it's real. The entanglement doesn't allow faster-than-light communication. You can't send information this way, but it reveals that quantum mechanics involves correlations deeper than classical physics can explain. Our photon might be entangled with a partner somewhere else in the universe, linked by invisible quantum threads. Through all of this, through the probability waves and quantum entanglements, through the flat geometry of expanding space, past countless planets orbiting distant suns, our photon continues. It has traveled so far, for so long, carrying its wavelength like a signature, its energy like a gift, moving through the darkness with absolute constancy. The universe grows older around it. Space expands. Entropy increases. But the photon persists, unchanged in its fundamental nature, a testament to the laws that govern all things. And somewhere ahead, though the photon cannot know it, something waits. An eye, perhaps. A detector. A grain of dust. Some surface where the journey will end and the photon's energy will be transferred, absorbed, transformed. The moment approaches, inevitable, though it might still lie years or millennia away. For now, the photon simply continues, as it has always continued, through the patient dark. Toward the ending. The photon's destiny. Our photon has traveled through the cosmic ocean for an age, and ahead, finally, lies something solid. The photon's trajectory, set at the moment of its last interaction countless light-years away, carries it inevitably toward this world. As it nears, the photon enters the planet's neighborhood of space, a region not entirely empty but filled with the star's influence. Every star creates a bubble around itself called the heliosphere. In our solar system, this bubble extends about 120 astronomical units from the Sun, roughly 111 billion miles, where the solar wind finally meets the interstellar medium and slows to a stop. The Voyager 1 spacecraft crossed this boundary, called the heliopause, in August of 2013, becoming humanity's first object to enter interstellar space. Our photon now crosses this same boundary in reverse, entering a stellar system after its long journey through the space between stars. The photon continues inward, toward the planet ahead. As it approaches, it might pass through the outer reaches of the star's planetary system, regions where comets orbit in vast clouds. In our own solar system, the Oort cloud, a spherical shell of icy bodies surrounding the Sun, may contain several trillion comets and extends nearly halfway to the nearest star. These frozen remnants from the solar system's formation orbit in the darkness, occasionally disturbed by passing stars or gravitational perturbations, sending some of them falling inward to become the comets we observe with their brilliant tails streaming across our skies. Our photon passes through such regions unseen, untouched by these ancient ice worlds. Drawing closer to the planet, the photon's speed remains exactly what it has always been, 299,792,458 meters per second in vacuum, a value physicists denote as c. This number is so fundamental that, since 1983, it has been used to define the meter itself. A meter is now defined as the distance light travels in 1,299,792,458 of a second. Our photon is, quite literally, the ruler by which we measure the universe. The photon approaches the planet's orbit, and here something begins to change. The planet possesses an atmosphere. When our photon enters this atmosphere, it encounters molecules of nitrogen, oxygen, and other gases. For the first time in perhaps millions of years, the photon interacts with matter. Its speed decreases slightly. Light travels slower through any medium than through vacuum. Our photon, entering the atmosphere, experiences its first deceleration in eons. As it descends through the atmosphere, the photon may scatter off air molecules, changing direction randomly. If our photon is blue or violet, it scatters more readily than if it were red or orange. This differential scattering, called Rayleigh scattering, is why Earth's sky is blue and why sunsets are red. Blue light scatters in all directions, filling the sky with color, while red light passes straight through to paint the horizon. Our photon, depending on its wavelength and the angle of its approach, might scatter multiple times, bouncing between molecules, or it might pass relatively straight down toward the surface below. The journey that was so direct in the vacuum of space becomes chaotic in this last brief passage through air. The atmosphere through which our photon descends is surprisingly thin. About 3/4 of the atmosphere's mass lies within about 7 miles of the surface, the part we call the troposphere, where weather occurs and where nearly all life exists. Above this lie progressively thinner layers, the stratosphere, containing the ozone layer that absorbs harmful ultraviolet radiation, the mesosphere, where meteors burn up, the thermosphere, where auroras dance, and finally the exosphere, gradually fading into space. Our photon has crossed from the realm of nearly infinite distances to this delicate envelope of air just a few miles thick. As the photon nears the surface, traveling now through the dense lower atmosphere, it approaches its final moment. Perhaps it will enter an eye. If our photon enters an eye, it will pass through the cornea and lens, focused onto the retina at the back of the eyeball. There, it will strike a molecule called rhodopsin, embedded in a rod cell, one of about 120 million such cells in a human retina. The photon's energy will cause the rhodopsin molecule to change shape, triggering a cascade of chemical reactions that generates an electrical signal. This signal will travel along the optic nerve to the brain, where it will be processed along with millions of other signals into the experience we call vision. A single photon can trigger this response. The human eye is so sensitive that in complete darkness, adapted rod cells can detect individual photons. Our photon, born in the heart of a star ages ago, will become a tiny spark of sight, a quantum of perception, before its journey ends. And then, in an instant that the photon experiences as no time at all, the absorption is complete. The photon ceases to exist as light. Its energy is transferred, its electromagnetic oscillation stopped, and its wave function collapsed. The journey that spanned light years and perhaps millions of years, that crossed the gulf between stars, that threaded through clouds of gas and past planets and through the final atmospheric veil, this journey ends in a single moment of interaction, as sudden and final as it was inevitable. The photon is gone. But its energy remains, transformed, passed on. Nothing in the universe is ever truly lost, only changed. And in this change, in this final transformation, the photon completes the purpose it never knew it had, to carry energy and information from one place to another, from one time to another, connecting the cosmos through the simple act of light traveling through darkness. The story ends. But somewhere, in the heart of a distant star, another photon is born, beginning its own journey through the infinite dark. And so the universe continues, woven together by light, connected across vast distances by these simple, tireless travelers, photons beyond counting, each one a messenger, each one a thread in the cosmic tapestry. Epilogue. The legacy of light. Though our photon's journey has ended, the story of light continues, infinite and eternal. Every moment, countless photons follow the same path, born in stellar cores, wandering through the dense interior, finally escaping to cross the void, and arriving at destinations throughout the universe. The night sky above you contains the accumulated light of billions upon billions of stars, each one sending forth roughly 10 to the power of 45 photons every second. That's a 1 followed by 45 zeros, a number so vast it exceeds the count of all grains of sand on all of Earth's beaches. Our Sun alone emits about 400 million photons each second, flooding the solar system with light. These photons carry more than just energy, they carry the entire electromagnetic spectrum, a rainbow far broader than human eyes can see. Visible light, the portion we evolved to detect, represents wavelengths between roughly 400 and 700 nanometers. But the electromagnetic spectrum extends infinitely in both directions. Radio waves can have wavelengths measured in kilometers, the size of mountains. On the opposite extreme, gamma rays can have wavelengths smaller than the nucleus of an atom, smaller than 10 to the power of -15 meters. All of these are photons, all traveling at the speed of light, all obeying the same fundamental laws, differing only in their energy and frequency. The universe speaks in this full spectrum, and we hear only the smallest fragment. Light has always been humanity's connection to the cosmos. When you look at the stars, you are quite literally looking backward in time. The light from the North Star, Polaris, takes about 430 years to reach Earth, meaning we see it not as it is now, but as it was in the year 1595, when Shakespeare was writing Romeo and Juliet. The stars of the Big Dipper range from about 80 to 125 light-years away. The light entering your eyes tonight left those stars before your great-grandparents were born. We see the universe not as it is, but as it was, a cosmic archaeological record written in light. Some of the photons reaching us have traveled distances that challenge comprehension. The farthest galaxy ever observed, as of recent measurements, lies about 13.5 billion light-years away, meaning its light has been traveling toward us for 13.5 billion years, nearly the entire age of the universe. We see this galaxy as it appeared just 300 million years after the Big Bang, when the universe was still young, when the first galaxies were just beginning to form. The photons from this distant galaxy are among the oldest light we can detect, cosmic messengers from the dawn of time itself. Light is also our fastest means of communication, and this creates profound limitations. If humans ever establish a colony on Mars, conversations with Earth would face a delay of between 3 and 22 minutes, depending on where the two planets are in their orbits. A question asked would receive no answer for at least 6 minutes, even at the closest approach. If we sent messages to the nearest star system, Alpha Centauri, we would wait 8.6 years for a reply, 4.3 years for the message to arrive, 4.3 for the response to return. The speed of light, despite being the fastest thing possible, is still slow compared to the vast scales of cosmic distance. Yet light also reveals the universe's deepest secrets. When astronomers split starlight into its component wavelengths using an instrument called a spectrograph, they see dark lines, specific wavelengths absorbed by elements in the star's atmosphere. Each element creates a unique pattern of lines, a spectral fingerprint. By studying these absorption lines, we can determine what distant stars are made of, their temperatures, their speeds, even the presence of planets orbiting them. We have never touched a star beyond our own sun, yet we know their composition with precision, all because of the information encoded in light. Every photon is a library, and we have learned to read it. The study of light also led to our understanding of the quantum world. In 1900, Max Planck proposed that energy comes in discrete packets, quanta, to explain how heated objects emit light. 5 years later, Einstein used this quantum idea to explain the photoelectric effect, showing that light behaves as particles, photons, when interacting with matter. This was the birth of quantum mechanics, a theory that has become the most precisely tested scientific theory in history, verified to astonishing accuracy. Measurements of the electron's magnetic moment agree with quantum theory to better than 1 part in a trillion, equivalent to measuring the distance between New York and Los Angeles to within the width of a human hair. Light showed us the quantum nature of reality. Light has also revealed the universe's ultimate fate. When astronomers measured the distances to far galaxies using supernovae as standard candles, and compared those distances to the galaxy's redshifts, they discovered something unexpected. The expansion of the universe is accelerating. Distant galaxies are receding faster and faster, driven by dark energy. If this acceleration continues, the universe will expand forever, growing colder, darker, and more empty. In the unimaginably distant future, perhaps 10 to the power of 100 years from now, even protons might decay, and the universe will enter an era where nothing exists but scattered photons, stretched to wavelengths larger than the observable universe itself, carrying infinitesimal energy across infinite space. The universe may end as it began, with light. But that ending lies so far ahead that it exists beyond meaning. For now, the universe is young, bright, filled with stars and possibilities. Light continues its work, connecting everything, carrying energy from stars to planets, from the past to the present, enabling sight, enabling life, enabling understanding. The infinite dance. Light beyond our story. As you drift toward sleep, consider the photons that surround you even now, in the darkness of your room. The walls around you, warmed by the day's heat, emit infrared photons. Light you cannot see but can sometimes feel as warmth. Every object warmer than absolute zero radiates photons according to its temperature, a relationship described by what we call blackbody radiation. Your own body, at a temperature of about 37 degrees Celsius or 98.6 Fahrenheit, emits roughly 100 watts of power as infrared light. You glow in the darkness, invisible to your eyes but bright in the infrared, radiating about 10 to the power of 18 photons every second from your skin. You are, quite literally, a being of light. This radiation follows a precise law discovered by Max Planck, relating temperature to the wavelengths of light emitted. The peak wavelength of radiation shifts as temperature changes. This is why heated metal first glows red, then orange, then yellow, then white as it gets hotter. Our Sun, with a surface temperature of about 5,500 degrees Celsius, emits most strongly in the yellow-green part of the spectrum, at a wavelength of about 500 nanometers. Cooler stars glow red, hotter stars shine blue or white. The entire universe can be read as a temperature map written in the language of light, each object announcing its warmth through the photons it emits. The cosmic microwave background, the afterglow of the Big Bang that fills all of space, consists of photons that have been traveling for 13.8 billion years, cooled by the universe's expansion to a temperature of just 2.7 Kelvin, or minus 270.45 degrees Celsius. These photons were once visible light, or even higher energy radiation, released when the universe became transparent about 380,000 years after the Big Bang. As space expanded, their wavelengths stretched, redshifted from visible light to infrared to microwaves. Today, about 400 photons from the cosmic microwave background exist in every cubic centimeter of space. Millions of them passing through your body right now, the oldest light in the universe, witnesses to the beginning of everything. Light also bends in ways that reveal the structure of the universe. When light from a distant galaxy passes near a massive galaxy cluster between it and us, the cluster's gravity acts as a lens, bending and focusing the light, sometimes creating multiple images of the same distant galaxy arranged in arcs or even complete circles called Einstein rings. The most massive galaxy clusters can bend light so strongly that they allow us to see galaxies that would otherwise be too distant and faint to detect. Gravity itself becomes a telescope, using curved spacetime to magnify the distant universe. Some of these gravitationally lensed galaxies are among the farthest and oldest objects we've ever observed, their light bent by clusters containing the mass of 1,000 trillion suns. In our own solar system, light has enabled us to explore worlds we may never visit in person. Every photograph from Mars, every image of Jupiter's storms, every glimpse of Saturn's rings reaches us as photons captured by spacecraft cameras and transmitted back to Earth as radio waves. Lower-energy photons traveling at light speed across planetary distances. The New Horizons spacecraft, which flew past Pluto in 2015, sent its data back to Earth at the speed of light, with signals taking about 4.5 hours to bridge the gap. Each image of Pluto's heart-shaped glacier, each measurement of its thin atmosphere, arrived photon by photon, reconstructed into data, revealing a world that had been little more than a blur for all of human history. Light has also allowed us to discover thousands of planets orbiting distant stars. Most exoplanets, planets beyond our solar system, are detected not by seeing them directly, but by observing the light they affect. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the star's light, causing a brief, subtle dimming we can measure. This transit method has revealed planets of every description: gas giants larger than Jupiter orbiting closer to their stars than Mercury orbits our Sun, rocky worlds with surfaces of molten lava, planets where it might rain glass sideways in screaming winds, and perhaps, someday, a world like Earth, where liquid water flows and life might exist. As of recent counts, we've confirmed over 5,000 exoplanets, with thousands more candidates awaiting verification. Light has shown us that planets are common, that nearly every star has worlds, that the universe is rich with possibilities. The photons reaching us from the most distant quasars, extremely bright galactic centers powered by supermassive black holes, have been traveling for over 13 billion years. These ancient photons show us the universe when it was less than 1 billion years old, when the first supermassive black holes were forming, when galaxies were young and actively colliding and merging. Some quasars shine with the luminosity of 1 trillion suns, so bright they can be seen across most of the observable universe. The light from these objects has traveled so far that the galaxies hosting them have likely evolved beyond recognition by now. The quasars may have quieted, their black holes dormant, their galaxies transformed by billions of years of evolution. We see their ancient light, but the reality we observe no longer exists, having transformed in the time it took the photons to reach us. Light even connects us to the very atoms in our bodies. Every carbon atom, every oxygen molecule, every trace element was forged in stars and scattered through space by stellar winds and supernova explosions. When you breathe, you inhale atoms that were once part of stars, cycled through the cosmos, incorporated into our planet during its formation 4.54 billion years ago. The calcium in your bones, the iron in your blood, these were created in stellar furnaces through nuclear fusion, the same process that creates the photons we've followed on their journey. We are, in the most literal sense, made of star stuff, as Carl Sagan so memorably said. The final rest. Light's eternal promise. As we approach the end of our journey together, let us consider one final truth about light. It is both the fastest and the most patient thing in the universe. A photon crosses the observable universe in what, to us, would be billions of years, yet to the photon itself, that entire journey occupies no time at all. This strange duality, urgency and patience, speed and timelessness, reflects something profound about the nature of existence. Everything that happens, happens in its own time, according to its own nature. The photon teaches us that the universe is in no hurry, yet wastes no time. Consider the light from the most distant objects we can observe. The James Webb Space Telescope, launched in December of 2021, can detect infrared light from galaxies so distant and ancient that their light has been traveling toward us for over 13 billion years. These galaxies formed when the universe was only a few 100 million years old, in an era astronomers call the cosmic dawn. The photons from these primordial galaxies left their sources before our Sun existed, before our solar system formed, before Earth coalesced from the disk of dust and gas surrounding the young Sun. They traveled through space while entire generations of stars were born, lived and died, while galaxies merged and evolved, while, on one small planet, single-celled organisms gave rise to all the complexity of life. And now, finally, those ancient photons arrive at our detectors, their journey complete, telling us stories of the universe's youth. Light has also revealed to us the structure of atoms themselves. In the early 20th century, physicists discovered that atoms emit light only at specific, discrete wavelengths, spectral lines that correspond to electrons jumping between defined energy levels. An electron in a hydrogen atom, for instance, can exist only in certain allowed orbits, and when it jumps from a higher orbit to a lower one, it emits a photon with precisely the energy difference between those levels. This quantization of energy, this discreteness at the heart of matter, was one of the great revelations of quantum mechanics. The Balmer series of hydrogen, a set of 4 visible spectral lines at wavelengths of 656, 486, 434, and 410 nanometers, appears in the light of distant stars and galaxies, proof that hydrogen atoms behave the same way everywhere in the universe, following the same quantum rules now as they did billions of years ago. The universe that light reveals to us is also surprisingly homogeneous on the largest scales. When astronomers map the distribution of galaxies across billions of light-years, they find that the universe looks roughly the same in every direction, a property called isotropy. And measurements of the cosmic microwave background show temperature variations of only about 1 part in 100,000 across the entire sky. This uniformity is puzzling. How did regions of space separated by distances so vast that light from one could never have reached the other end up at almost exactly the same temperature? The theory of cosmic inflation proposes that in the first tiny fraction of a second after the Big Bang, perhaps 10 to the power of minus 36 seconds, the universe expanded exponentially, growing by a factor of at least 10 to the power of 26 in an inconceivably brief moment. This rapid expansion would have smoothed out any initial irregularities, creating the uniform cosmos we observe today, while also stretching quantum fluctuations to cosmic scales, providing the seeds from which galaxies would eventually grow. Light has also shown us that the universe is older than any of its contents. The oldest stars we've found are approximately 13.2 billion years old, formed when the universe was only about 600 million years old. We know this by measuring their composition. These ancient stars contain almost no elements heavier than helium, because they formed before many generations of stellar deaths could enrich the interstellar medium with carbon, oxygen, iron, and other heavy elements. They are called population 3 stars in theoretical models, though we've never directly observed a pure population 3 star. Those would contain absolutely no heavy elements at all, only the hydrogen and helium created in the Big Bang. The stars we see are their descendants, slightly contaminated with heavier elements, but still ancient beyond imagining, some of them shining for longer than Earth has existed. As you settle deeper into rest, consider this: the photons that entered your eyes today and allowed you to see, to read, to recognize faces, to navigate your world, each carried a tiny amount of energy, about 3.5 electron volts for a photon of green light. An electron volt is an incredibly small unit of energy. A single electron volt is about 1.6 times 10 to the power of minus 19 joules, so small that it would take about 6 billion of them to equal the energy of a flying mosquito. Yet this minuscule energy is enough to trigger a chemical change in the rhodopsin molecule in your retina, initiating a signal cascade that your brain interprets as light. Vision is possible because evolution discovered how to detect and process individual photons, to extract meaning from these quantum messengers, to build an entire model of reality from tiny packets of electromagnetic energy. The fact that you can see it all is a testament to the universe's deep interconnectedness. Stars create light, biology learns to detect it, consciousness emerges to interpret it, and understanding follows. Light has given us not only vision and knowledge, but also a sense of our place in the cosmos. When Galileo first turned his telescope to the heavens in 1609, he saw moons orbiting Jupiter, proving that not everything in the cosmos circles Earth. He saw that the Milky Way is composed of countless individual stars, that the moon's surface is rough and mountainous, that Venus shows phases like Earth's moon. Each observation was made possible by light, photons from distant objects, focused by glass lenses, entering his eyes and revealing truths that changed humanity's understanding of existence. In the 4 centuries since, our instruments have grown vastly more sophisticated, but the principle remains the same: we learn about the universe by studying light. Every telescope, every detector, every astronomical instrument is fundamentally a device for collecting and analyzing photons, for extracting the information they carry about their sources and their journeys. And now, as you approach sleep, as consciousness begins to fade and thoughts become dreamlike, know that the story of light continues without pause. Above you, even as you rest, photons from the sun, now on the far side of Earth, are illuminating other lands, driving photosynthesis in distant forests, warming other oceans, enabling other eyes to see. Throughout the galaxy, throughout the universe, in numbers beyond comprehension, 10 to the power of 88 photons might exist in the observable universe at any given moment. Light carries out its work, connecting all things, enabling all complexity, making possible everything from the simplest chemical reaction to the emergence of consciousness itself. The photon whose journey we followed was just one single quantum of light among uncountable multitudes. Yet in following that one photon from birth to absorption, we traced the outline of universal laws, explored the nature of light and matter, touched on the deep principles that govern existence. That photon story is every photon's story, and every photon's story is, in some sense, the universe's story. Energy flowing from sources to sinks, from stars to space, from order to entropy, carrying information, enabling change, connecting the cosmos across space and time. You are part of this story. The light that sustains you, that allows you to see, that warmed your world today, this light connects you to the sun, and the sun to the galaxy, and the galaxy to the universe beyond. You are made of atoms forged in stellar cores, organized by processes powered by light, animated by chemistry driven by energy that once lived in the heart of a star. You are not separate from the cosmos but woven into it, a temporary pattern of matter and energy, conscious for a brief moment, able to contemplate your own existence and marvel at the universe that created you. Let this be your final thought as sleep takes you, that you are held by the universe, part of its ongoing story, connected to everything through light and gravity and the shared origin of all matter in the Big Bang. The photons will continue their journeys. Stars will continue to shine. And consciousness, having emerged once, may emerge countless times across the cosmos, wherever conditions allow, each instance able to look up at the stars and understand through light the nature of its own existence. Rest now, knowing you are home in the universe, that the cosmos is not alien or hostile but the very source of your being, that every atom in your body and every photon that touches your eyes is part of one great interconnected whole. Let the ancient light of distant stars be your lullaby, the patient constancy of physical law be your comfort, the knowledge that you are woven into something vast and beautiful be your peace. The story of the photon is complete. Your story continues for now, in dreams and rest and the quiet restoration of sleep. And tomorrow when you wake, the sun will have risen and new photons, born ages ago in the solar core, finally freed to cross space, will arrive to begin their work again, illuminating your world, making vision possible, sustaining life, connecting you to the cosmos through the eternal, simple miracle of light traveling through darkness. Good night, traveler. Rest well, knowing you are part of something infinite and eternal. The universe holds you gently, and light connects all things. Sleep now. The photons will continue their journey. And so will you. The story ends here, but light goes on forever.